Hey guys, today we're going to learn about the antiderivative, which is basically the reverse operation of differentiation, also called the integration of a function. So when we're finding the derivative of a polynomial type function, this is what we do. We multiply the coefficient by the power of each term, and then you subtract 1 from the power of each term. So that's just basically the power rule of differentiation. Now with integration, you're doing the opposite of each of these operations and in the reverse order. So first we would add 1 to the power of each term, and then you divide the coefficient of each term by the new exponent. So let's look at these examples here. We have here our function f of x. If you were to go backwards and integrate it, that would make it capital F of x. And then if you were to go forwards, that's the derivative of f of x. So if we have 2x, which is our function, if we integrate that, then we would have to add 1 to the exponent, so that would be 2, and then divide by 2, so that would give us x squared. And think about it, if you were to differentiate x squared, you get 2x. And then the derivative of 2x is 2. So if we're starting with the derivative, which is 6x, then we would have to add 1 to the exponent, so 6x squared, and then divide by that new exponent, giving us 3x squared. And if you integrate this function, we would have to add 1 to the exponent, so 3x to the third, and then divide by the new exponent, which is x to the third. So you kind of see how this works. The derivative of x to the third is 3x squared, and the derivative of 3x squared is 6x. So we're essentially just working backwards. Now, just so that you understand the notation and the terms that we use when it comes to integration. This what kind of looks like a long S here. This is the symbol for integration. That means to integrate the function, just like when you see d dx, that means to differentiate the function. So it is the operator. Then whatever is inside of our integral, because this is called the integral, that is called the integrand. That is what we are integrating. Then you'll always see at the end of every integral what's called the variable of integration. That means that we are integrating with respect to x. So that is how you understand, or that's how to read an integration problem. So let's look at one more thing before we start practicing integration. If you were to find the derivative of x squared, we get 2x. If we were to find the derivative of x squared plus 1, we get 2x. And if we were to differentiate x squared plus pi, we get once more 2x. Now here's the problem. When we integrate, we don't know if there was a constant that was added at the end, because when you integrate a derivative, it's not taking into account that particular constant. So whenever you are integrating a function, you always add a plus c at the end. This is the constant of integration. This means that when you integrated your function, there may or may not have been a value of c at the end, some constant. So for example, we have here, we want to integrate 4x to the third plus 5x squared minus x with respect to x, because that is what the dx represents. So first we have 4x to the fourth, because I have to add 1 to my exponent and then divide by the new exponent, plus 5x to the third, because I'm again adding 1 and then divide by the new exponent, minus x squared and divide by the new exponent. Then of course the plus c. At this point, simplify as much as you can. The only thing that we can simplify is that these 4's will cancel out. So my answer would be x to the fourth plus 5x to the third over 3 minus x squared over 2 plus c. And if you're ever unsure if when you integrated what you got is correct, you can take the derivative and make sure that it matches what is inside of the integral, or make sure it matches the integrand. So let's look at a couple examples. First we want to integrate 3x squared plus 2x plus 3, another polynomial type equation. So we just add 1 to all of these exponents and then divide by the new exponent. So 3x to the third over 3 plus 2x squared over 2 plus 3x, because here we have a constant, and we know that when we derive something like a coefficient with x, we get the constant, so we just add the x, and then plus c. Simplify would give us x to the third, because the 3's would cancel, plus x squared, because those 2's would cancel, plus 3x plus c. And this would be my integrated function. And again, you can test it to make sure that it equals to the integrand. The derivative of x to the third is 3x squared. The derivative of x squared is 2x. The derivative of 3x is 3. And the derivative of any constant would be 0. So this is good. Now over here we have x to the third plus 2x squared minus 4x all divided by x. When you are integrating functions, it is so much easier if you can first rewrite your function as a polynomial type function. So in this particular case, I would divide every single term in the numerator by x. So before even integrating, I am rewriting. So this would be x squared plus 2x minus 4 dx. You always want to make sure if you are rewriting an integral that you put that variable of integration at the end. Otherwise, it is not complete. And a lot of the times in FRQs, they look for it that you have that variable of integration. If you don't, sometimes they take off a point because technically this problem is not written completely. So now we're going to integrate. So for each one, we add the exponent and then divide by the new exponent. So that would be x to the third over 3 plus 2x squared over 2 minus 4x plus c, which then we could rewrite as x to the third over 3 plus x squared, since those 2's would cancel, minus 4x plus c. And this would be my final answer. Once more here, we have the integral of x plus 2 times 2x minus 3 dx. Now, unlike derivatives where we have product rule, quotient rules, etc., integration doesn't have that many rules at all. In fact, you have to get a little bit creative. And most of the time, it's just rewriting the function in a polynomial type form so that we can integrate more efficiently. So before I integrate, I would have to multiply all of this together. So let's do that. So we're going to distribute the x first, which would be 2x squared minus 3x. Then distribute the 2 plus 4x minus 6 dx. Combine like terms, we get the integral of 2x squared plus x minus 6 dx. And now we're ready to integrate. Remember, we're adding 1 to the exponent, divide by the new exponent. So this would be 2x to the third over 3 plus x squared over 2 minus 6x, and don't forget the plus c. And this would be my final answer, since there's nothing here that we can actually simplify. Over here, we have 2 divided by the square root of x. Now, this is the same thing as saying 2 over x to the 1/2. Again, this is going to be very difficult to integrate if you leave it like this. So I'm going to move that x to the 1/2 up to the numerator. So what I'm actually going to integrate is 2x to the negative 1/2 dx. We're going to add 1 to the exponent. Adding 1 would be 1/2, so that would be 2x to the 1/2. And then we're going to divide by the new exponent, which is 1/2. Whenever you're dividing by a number that is a fraction, really what we're doing is we're multiplying by the reciprocal. So this is 2x to the 1/2 times the reciprocal of the fraction, which is 2. leaving me with a final answer of 4x to the 1/2 plus c. You can either leave it like this, or you can also write 4 square root x plus c. And that would be our final answer for this integration problem. Now there are a couple of special cases which we're going to go over now. The first one is to recognize when you have the antiderivative of the ln function. If we were to try to integrate this, we have 3 over x dx. This can be rewritten as 3x to the negative 1 dx. If I add 1 to the exponent, we would get 3x raised to the 0, and then divide by 0, which is impossible. So that process of integration does not work. If that ever happens, that means that what you have there is the ln function. And just so that you can remember, right, the derivative of ln is 1 over x. Now I actually wrote this incorrectly. This should read 3 ln of x. Now if you try to find the derivative of 3 ln x, then remember that coefficients just kind of tag along. So we would have 3 times the derivative of the ln of x, which is 1 over x, which gives me 3 over x, which is exactly what we had here. So if we were to integrate this number 3, this is just a coefficient. This is the same thing as saying 3 times 1 over x, right? So what we could have done is move the 3 on the outside, since coefficients just kind of tag along. So this could have been rewritten as 3, the integral of 1 over x, which is equal to 3 ln x plus c. So that's how you would integrate an ln function. So let's try with these examples here. We have 2x over x squared, which can be simplified to 2 over x dx, since a pair of those x's would cancel out. Now this 2, this is a coefficient, so we can move it to the front. So this is the same as saying 2 integral of 1 over x dx. Again, you have to be able to recognize that this is the ln function. So this is 2 ln of x plus c. Let's try that with this last one here. We have x over y dy. Now if you have two variables, you have to look at the variable of integration. It's in terms of y. That means that this x here, this is just a constant. So we can move that, because that's considered kind of like a coefficient, we can move it to the front of the integral. So this is the same thing as saying x, the integral of 1 over y dy. Again, this is the ln function. So this is going to equal to x ln of y plus c. Now just as a quick side note, keep in mind that when you're finding the antiderivative of any ln function, the derivative of any ln is the derivative of what's inside of the ln over what's inside. So that's why the ln of x is 1 over x, because the derivative of x is 1 and we put it over x. So like if you had, for example, if we kept it like this, right, in this example here, 2x is the derivative of x squared, right? And so that means that this is the same thing as saying the ln of x squared plus c. But because of rules of log, any exponent here could be moved to the front. So this is the same thing as saying 2 ln of x plus c, which gives us the same answer that we got before. So whichever way you choose to approach it is fine, as long as you recognize that if the numerator is a derivative of the denominator, that is the ln of the denominator. Let's look at now a little bit of trig. So this is what we know. We know that the derivative of sine is cosine, and the derivative of cosine is negative sine. So now if we're working backwards, the integral of cosine is sine, right? Because we're going backwards, plus c. But the integral of sine, right, here if we were to go backwards, we have this negative here. So the integral of positive sine would give me negative cosine x plus c. So let's practice with a couple of examples. We have here 2 sine x plus cosine x dx. If you were to integrate that, the integral of sine x is negative cosine. Remember, coefficients just tag along. So this is negative 2 cosine x plus the integral of cosine, which is sine x. And then, of course, plus c. So that's it. This would be my answer. Nothing else you can really do with that. Now, integrating this, think of this as like a polynomial. You're doing one piece by piece. So we have the integral of x squared, which would be x to the third, because I'm adding 1 to my exponent, over 3. And the integral of sine is negative cosine. Or you can think of it as the integral of negative sine, which would just be cosine. So whichever way you choose to think about it, I like to do minus, and then the integral of sine, which is negative cosine, so plus cosine x, and then of course plus c. And that would be my answer. Last one here, not last one, but the next one, we have the square root of x plus sine x. First, I would rewrite this using my exponents. So this would be the integral of x to the 1/2 plus sine of x dx. So my answer here, we would have to add 1, so x to the 3 over 2, because I have to add 2 over 2 to be able to add 1 to that exponent, multiply by the reciprocal of the fraction, so 2 over 3, plus the integral of sine, which is negative cosine x, plus c. And now we can rewrite this as 2 over 3 x to the 3 over 2 minus cosine x plus c. And this would be my final answer. Last one here, we have 4x minus 3 cosine x. The integral of 4x would be 4x squared over 2. And then minus 3 and the integral of cosine, which is sine x plus c, which this can be rewritten as 2x squared minus 3 sine x plus c. And this would be my final answer. Now, there are some cases where you will have to solve for the constant of integration, meaning solving for c. So there are a lot of questions, and these are called differentiable equations, where we're going to work backwards to get the actual f of x function, including the constant of c. So you're given all of this information. We have f double prime of x is equal to 2, f prime of 2 is equal to 5, and f of 2 is equal to 10. So in order to get f of x, which is what we're trying to do here, we're going to first take our second derivative and integrate it in order so that we can get the first derivative. So we start off by integrating f double prime of x, which is equal to 2. So I'm integrating both sides of this equation. So this gives me f prime of x, which is equal to 2x plus c. Now we are told that f prime of 2 is equal to 5. So I'm going to plug in the 2, which is 2 times 2 plus c, and make it equal to 5. This gives me that 4 plus c is equal to 5. Therefore, c is equal to 1. So f prime of x is going to equal to 2x plus c, which we got to be 1. Now we integrate both sides again. And this gives me f of x is equal to 2x squared over 2 plus x plus c. Now we are told that f of 2 is equal to 10. So we plug in the 2. F of 2 is equal to, and I forgot here to cancel out these 2's. So 2 squared plus 2 plus c is equal to 10. 2 squared is 4, plus 2 is 6, plus c is equal to 10. That means that c must equal to 4. So now our function f of x is going to equal to x squared plus x plus c, which is 4. And that's just by looking at this function here. And this would be my actual f of x function. Let's try that with another example. We have here f double prime of x is equal to x raised to the negative 3 over 2. F prime of 4 is equal to 2. And f of 0 is equal to 0. So first we're going to start off by integrating both sides of f double prime, which would give me f prime of x is equal to, now I have to add 1, so I'm going to add 2 over 2, which is x to the negative 1/2 multiplied by the reciprocal of that fraction, which is negative 2. So I get that f prime of x is equal to negative 2x raised to the negative 1/2 plus c, which I can rewrite as negative 2 over the square root of x plus c. Now we are told that f prime of 4 is equal to 2. So f prime of 4 is equal to negative 2 over the square root of 4 plus c is equal to 2. Now negative 2 divided by the square root of 4 is the same thing as saying negative 2 divided by 2, which is negative 1. So we get negative 1 plus c is equal to 2. To solve for c, we would add the 1, so c is equal to 3. So that means that f prime of x is equal to negative 2. Now I'm looking at this, but I'm rewriting it so that I could be able to differentiate it. Integrate it. So x raised to the negative 1/2 plus c, which is 3. Now we integrate both sides to get f of x. So f of x is going to equal to negative 2x. I'm going to add 1, so plus 2 over 2, which is 1/2, multiplied by the reciprocal, which is 2, plus 3x plus c. This could be rewritten as negative 4 square root of x plus 3x plus c. Now we are told that f of 0 is equal to 0. So f of 0 is going to equal to negative 4 times the square root of 0, which is 0, plus 3 times 0, which is 0, plus c is equal to 0. So in this case, c is equal to 0, meaning that we have no c. So our final answer for f of x would equal to negative 4 square root x plus 3x. And that would be our final answer. Now let's look at a couple of partial FRQs. This first one says, an evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. The growth rate during those 6 years is approximated by the differential equation dh over dt is equal to 1.5t plus 5, where t is the time in years and h is the height in centimeters. The seedlings are 12 centimeters tall when planted. So part A says to find the value of the differential equation above when t is equal to 3. Using correct units of measure, explain what this value represents in the context of the problem. Now, whenever you see notation like this, dh dt, this is a derivative equation. So this is a rate, and it even tells you here that this represents the growth rate. So if you are evaluating for something like this, now normally we like to use function notation, but it's hard when it's written like that. The notation would be dh dt. We put a bar, and then we put the number for which we are evaluating for in the bottom corner. So this is kind of like f of 3 type situation. That's what this means. This is the value of dh dt for when t is equal to 3. So we plug in the 3, 1.5 times 3 plus 5. 1.5 times 3 is 4.5, and 4.5 times plus 5 is equal to 9.5. Now remember the units. This is height over time. So this is centimeters per year. So when we are trying to explain what this means in the context of the problem, since I plugged in 3, this is at 3 years. So we would say 3 years after being planted. Remember that this is a rate. So you have to explain that this is a rate. So we would write the shrubs are growing at a rate of 9.5 centimeters per year. Now for this next one, it says to find an equation for h of t. So now we're going backwards. We have the derivative, but we want the function, the height of the shrubs at any year t. Then determine how tall the shrubs are when they are sold. So first let's try to evaluate, or rather to find the equation for h of t. So that means that I have to take my dh dt, which is equal to 1.5t plus 5, and integrate both sides. When we integrate dh dt, remember the rate, that means that we are getting the function, so h of t, which is going to equal to 1.5t squared over 2 plus 5t plus c. Now the problem here is that I don't know what c is. That's what I need. But remember what I've said in the past. All FRQs give you all the information that you need. There will never be anything written that you will not use. And here we are told that the seedlings are 12 centimeters tall when planted. So this means that at t is equal to 0, the height is equal to 12. So I could plug in t for 0. So h of 0 is equal to 1.5 divided by 2 is 0.75, so 0 squared, plus 5 times 0 plus c is going to equal to 12. This is 0, this is 0, so that means that c is equal to 12. So for h of t is going to equal to 0.75 t squared plus 5t plus 12. Because that's the first part of this question, is to find an equation for h of t. Now we're going to determine how tall the shrubs are when they are sold. It says here that we sell them after 6 years of growth. So that means that we want to find h of 6, because that's when they're sold. So this is going to equal to 0.75 times 6 squared, which is 36, plus 5 times 6, which is 30, plus 12. 0.75 times 36 is equal to 27, plus 30 plus 12, which is 42. So when we add this together, we get 69. And this is a height. This is not a rate, because we just solved for h of t. So 69 centimeters. So the height of the shrubs when they are sold is 69 centimeters. Now let's go back to particle motion. Let's look at a particle motion question. Now remember that the derivative of position is velocity and the derivative of velocity is acceleration. Therefore, if you were to go backwards, the antiderivative of acceleration is velocity and the antiderivative of velocity is position. In this particular example, we are told that a particle moves along the x-axis at a velocity v of t is equal to 1 over the square root of t. for t is greater than 0. At time t is equal to 1, its position is 4. So the first part of this FRQ states what is the acceleration of the particle when t is equal to 9. Since we're trying to find acceleration, acceleration is the derivative of velocity. So first I am going to rewrite velocity so that it is easier for me to differentiate. Velocity is equal to t raised to the negative 1/2. Since it is a square root, the exponent is 1/2, and in the denominator we make that exponent negative. So that means that a of t is going to equal to negative 1/2 t raised to the negative 3 over 2. Now this I'm going to rewrite as negative 1 over 2. And then this, I'm putting the t in the denominator because it's a negative exponent. The 2 in the bottom, that means it's the square root of t. And then the exponent 3, right, the numerator, that's the power. So I am trying to find a of 9. That's a 9, and that's an a. Let's make this longer. There you go. A of 9. So this is going to be negative 1 over 2 times the square root of 9 cubed. I usually like to do the root first, although it doesn't necessarily matter if you do the power and then the root, but I like doing the root because the numbers are smaller. So negative 1 over 2, the square root of 9 is 3, and 3 raised to the third is 27. And 2 times 27, that would give me negative 1 over 54. And don't forget, if we're given units, we would write the units. In this case, we have no units, so that's it. Our answer is negative 1 over 54. But remember, since this is acceleration, if we were to be given units, it would be the unit of measurement of length over time squared. Now for part B, we are trying to find the position of the particle when t is equal to 9. So we have here again our velocity equation, which we wrote here as v of t is equal to t to the negative 1/2. Since we're trying to find position, we would have to integrate because we're going backwards. So v of t is equal to t to the negative 1/2. I'm going to integrate both sides, and don't forget to include that variable of integration, so dt. So this is going to give me p of t for position is going to equal, I'm going to add 1 to my exponent, so t raised to the 1/2, and then, and then we would divide by the new exponent. So divided by 1/2 is the same thing as multiplying by 2, since we're multiplying the reciprocal of 1/2, and then of course plus c. I can't find the position of the particle when t is equal to 9 yet because I don't know c. But here in the problem, it tells me that at time t is equal to 1, its position is 4. So that means that I can find p of 1, which is 2 times the square root of 1 plus c, and it's going to equal to 4. So this is 2 times 1, which is just 2 plus c is equal to 4. Therefore, c is equal to 2. So p of t is equal to 2 square root of t, right? And I'm looking here, I'm just replacing c now. So plus c, which is 2. I'm trying to find p of 9. So now I'm going to plug in the 9. 2 times the square root of 9 plus 2. The square root of 9 is 3, so 2 times 3 is 6 plus 2, so its position is 8. And that's the introduction to integration, or the antiderivative.